are, by nature, explorers. The same curiosity that sends us to the stars at the speed of thought urges us to go there in reality. And whenever we make a great new leap, we elevate humanity, bring people and nations together, usher in new discoveries and new technologies. So remember to look up at the stars and not down at your feet.
Right, so hi to everyone. I am Ugnė and I'm an astronomer at Durham University. I'm very excited today to have this opportunity to give a brief introduction into what astronomy is all about as a science, as a job, as a career, and just a brief introduction to myself if you've just joined. So I finished my master's studies in physics and astronomy at Durham as well, and now I'm in my final fourth year of PhD, finishing my astronomy PhD. So just before we go into the talk, I will quickly go through the terminology, if this now works. Yep. So some of you might have heard terms like astronomer, astrophysicist, cosmologist, and really what is the difference between them? So to be honest, I was confused about it before I started my studies at university. So just to clarify this, astronomer and astrophysicist are basically interchangeable terms. So I'm an astronomer, I'm also an astrophysicist. And cosmology is basically a branch of astrophysics that deals with the largest structures, the universe as a whole. So some cosmologists deal with making simulations of the universe, how it forms, how it evolves. And astronomy and astrophysics is just a space science that tries to make sense of the universe that we live in and what physical processes happen. So let's start. Today's talk will be split into two sections. So first is a bit more technical, a bit more sciencey, and the second one is more of a human aspect of it. So I had a chat with Will and Ross from UK Astronomy, and we decided that there are a few questions that most of you might be interested in. So first, how do astronomers figure out properties of very distant objects? So if you see, let's say, an article online that say these are massive galaxies forming stars very quickly and have a very active black hole, how do we actually know these things? Then looking into second part would be, why do we need many different telescopes? So some of you might have heard of Hubble Space Telescope or Very Large Telescope, and there are so many of us, so why do we need so many? Then we'll look into a brief introduction into dark matter and into some of the research that I'm doing. So my research focuses on galaxy formation and evolution, looking into the distant universe. And after which we might have a brief discussion or Q&A for a few minutes. And then we'll go into a more chilled out session to what do astronomers do every day and what is it like observing with some of the largest telescopes in the world. So now we start with the galaxy structure. So in the simplest terms, galaxies are just formations of many of stars. And in the middle, we have the bulge, which is the central round region, spherical region, where most of the older, colder stars reside. And if we look at the disk, it has this nice spiral structure. So throughout this talk, I'll mainly focus on spiral galaxies. So these galaxies have these disk structures with nice spiral arms. And we see, if we look at the edge-on version on the right, it's a much thinner formation. So imagine having pizza dough and spinning it around and it flattens into a disk. That's what kind of happens in galaxies as well. And these are the main two components in galaxies that hold most of the mass. We have some globular clusters around as well and stellar halo, which are parts of the galaxy, but most of the visible mass is in the bulge and the disk. And we'll also go into some detail about dark matter later on in the talk. So to explain how astronomers look into galaxies, I chose to look at the Whirlpool galaxy. So I've seen some of you have pictures on the Facebook group that you've taken of Whirlpool galaxy, and those look amazing. And this is a photo done by Hubble Space Telescope in the optical. Now, what do I mean by the optical? So let's have a quick recap into electromagnetic spectrum. So our eyes see visible light. So our eyes detect this range of wavelengths that is not really the whole spectrum, just a small part of the spectrum. The spectrum ranges from very long wavelengths, which are radio waves, to very short wavelengths and very energetic wavelengths, which are X-rays and gamma rays. And we use that in every day. So radio are used to broadcast radio and television. Microwaves, of course, are used in cooking and aircraft communication and many other devices. Infrared is used, let's say, in TV remotes or night vision goggles and stuff like that. So when we go to more energetic waves, we see visible light, and that's the light that, again, our eyes can detect and we can make sense of it. If we go to more energetic light, it's ultraviolet, and you might have heard about it from sun cream ads or something like that, because UV radiation gets absorbed by our skin, but most of the UV radiation is blocked by the atmosphere. And if we go to the most energetic radiation, this is X-rays and gamma rays, and in small doses it's used in medicine, and the radiation that's coming from the universe gets mostly blocked by our atmosphere, which helps us, life on Earth. So as I said, energy increases as this wavelength decreases. So if you imagine holding a rope and making it vibrate up and down, the more energy you put into vibrating that rope means that you'll get more and more up and down motion, which means shorter wavelength. So this is similar is happening with light. The shorter the wavelength, the more energy it has. So now if we look at the galaxy again, at the Whirlpool galaxy, this galaxy is around 30 million light years away, and it's a merger galaxy, right? So it has a spiral galaxy in the middle and a dwarf companion galaxy on the right. And just by looking at this galaxy in the optical in more detail, we see that the dwarf galaxy has a yellower color than the spiral galaxy. This indicates to us that these are older stellar populations with much older and cooler stars in it, while the blue and the purple light in the spiral galaxy indicates that there is star formation occurring. So especially these purple dots around the spiral arms show us the stellar nurseries, so where the stars are born. And we can see that there's quite a bit of star formation. But also what we can see is these black streaks, and these are dust grains and dust structures in the galaxy, and they absorb visible light, and we're not able to probe past it. So what happens if we look at the more energetic radiation? So if we look at UV rays or X-rays. So here I'm showing the images of the same galaxy, and in ultraviolet UV radiation, we see it traces star formation. So the spiral disk is seen in UV emission because that's where hot, young, massive stars are born. And we see that the companion dwarf galaxy is not detected in this image because it doesn't have these regions where young stars are forming. So it's a much older population of stars in this galaxy. And if we look at X-rays, which is even more energetic emission, X-rays trace most hot extreme events, so accreting black holes, emit this radiation because the environment is so hot and extreme around black holes. So we see here the central region where the black hole in this galaxy is, it's emitting these X-rays. If we look at longer wavelengths, we go into infrared, which is indicated in red here at the bottom. And if we look in near infrared and mid infrared, so these are just different wave bands, we see quite different structures as well. So let's focus on the MIR, which is the mid infrared. We see two very different colors, and the green color indicates, again, very old stellar populations and colder stellar populations. So old stars in there. While the red traces hot dust, and hot dust in these galaxies indicates star formation. So we see that these galaxies, even though they're nearby, they have very different environments. And quickly to mention radio are the longest waves. They trace, again, accreting black holes and supernova remnants, so when galaxies, stars, explode. So we can get a very different picture of the same galaxy if we look at it through different wavelengths. And if we look at not just the whole wave band, but a very narrow range in wave bands, so a narrow range in wavelength, we can see the features that are within that wavelength. And that, for example, lets us look at the gas within this galaxy. So here we see in blue the gas extent in this galaxy, and we see it's much more extended than the optical image that is overlaid on top. And that is showing that this gas is being stripped from the galaxy disk into this much bigger region because of this interaction between the two galaxies. So looking at the same object in these different wavelengths allows us to build a much more complete image of what processes are occurring in this object. So to answer this first question, how do astronomers figure out properties of very distant objects? Well, we need to look at the multiple wavelengths, at the whole electromagnetic spectrum to get this complete picture of the object that we're seeing. We need X-rays and ultraviolet emission, which trace the very hot extreme events and the formation of very hot young stars. We need optical that traces the stellar populations that let us see the older stars and the newborn stars. If we look into infrared, it traces dust and gas, and radio, as we mentioned, traces supernova remnants and accreting black holes. So to get all of these observations, we might need different telescopes. So to answer the second question of why do we need many different telescopes? Well, we want to observe these objects. We want to get the emission from different wavebands. So for example, optical and near infrared emission is traced by the Very Large Telescope, which is in Chile. These are actually 4 telescopes working in the optical near infrared regime. Also, there are Mauna Kea observatories, so there's multiple telescopes in Hawaii on Mauna Kea that also span multiple wavelengths. And I'll talk about these later in the second section about going observing at these facilities. We also have radio telescopes. So ALMA is a telescope array in Chile, and VLA is a very large array in America. And we see that these look very different. These are radio dishes, and that's because getting detections of this emission requires very different techniques and very different instruments. And that's why these telescopes look very different. And we do need these different telescopes to get this emission. And finally, of course, we know there are telescopes in space. So of course, there are more than just these two, but for example, there's Chandra Space Telescope, which takes observations in X-rays, and Hubble Space Telescope takes observations in the optical. But why do we need them in space? Why do we need telescopes on the ground? Well, that's because there's different transmission in the atmosphere. So as we mentioned before, atmosphere blocks out most of the gamma rays, X-rays, ultraviolet, and it's shown by these lines where in the atmosphere they're being absorbed. And similar thing happens in the infrared wavelengths. But we see these optical windows and radio windows where there is emission coming down to the ground. So that's why we can use ground-based telescopes for these observations. For observations in the gamma rays and X-rays, we need telescopes in the space. So just to answer these two questions, we need to study the emission at multiple wavelengths, which means multiple energies, to fully understand what is happening in galaxies, what physical processes form them, how they evolve. And observations have to be done at different wavelengths, which requires very different techniques. And some emission is not transmitted through the atmosphere. That's why we need to send some telescopes to space. So now that we've talked about these basics of astronomy, let's look into what I'm doing, so galaxy formation and evolution, and let's see what dark matter is. So as we mentioned, we might think of galaxies as containing dust, gas, and stars, right? Well, it turns out that most of the mass in galaxies is invisible. Now, how do we know this, and what does this mean? Well, most stars and galaxies are concentrated towards the middle. So the gravitational pull is strongest in the middle and decreases with distance. That means that stars in the inner regions have to rotate around the galaxy faster than those in the outskirts. However, in the 1970s, astronomers found that the rotation in the outskirts was not declining. So here I'm showing a video. On the right is what we see. There is no decline in velocity with the distance from the center, while what we might expect from the visible matter in the galaxies is shown on the left. So these galaxies should fly apart. We should not be seeing these nice structures that are visible in the universe. There must be matter that does not reflect or absorb light, which holds galaxies together through gravity. And we call that dark matter. Now, since then, it has become a fundamental component in galaxy formation and evolution. Its gravitational pull is thought to drive gas to collapse and form stars, just like our own sun, and through that, galaxies, just like our own Milky Way. So those studies of these local systems were possible in the last century. Only recently, these studies were possible at very distant universe. And by looking at very distant universe, we are looking back in time. So for example, if a galaxy is 9 billion light years away, we see the light that was emitted by the galaxy 9 billion years ago. And that is what my research is doing, looking at these galaxies that are billions of light years away. And here are some images of these galaxies. Of course, they don't look as nice as the galaxies that we see in the local universe, but we do get a lot of information from these. So as I mentioned before, by looking at the light profiles, we can infer the distributions of gas, stars, and dust, which gives us the total visible mass of the galaxy. And by looking at these very narrow wavelength ranges, we can see the features that some of the elements produce, and by that create a three-dimensional image of a galaxy and see how it is rotating. So just to show what's happening, here we're going back in time. So from our perspective, we're going further into the universe, so further back in time. And here are some of the galaxies that I am studying, which will be shown soon in squares. Should be right now. Yes, so these are some of the galaxies. By looking at the features that we see from a method called spectroscopy, we can create these maps where red shows the matter that's moving away from us and blue shows the motion that is moving towards us. And so in that way, we can infer the rotation of the galaxy and the speed at which it's rotating. Combining these observations with the mass that we inferred from the visible mass, we can tell how much dark matter, this invisible matter, must be in these galaxies to make them spin faster. And my research with our collaborators indicates that even 9 billion years ago, these galaxies were dominated by dark matter, so they have 70 to 80% of their total mass completely invisible to us. But we see its effect through its gravitational effect. So that has implications to cosmological simulations. It adds constraints into how galaxies and dark matter evolves by looking at galaxies in the very distant universe and comparing them to the galaxies that we see here close to us locally. We can assess the evolution that has happened in those 9 billion years and put constraints on some of the simulations. So for example, here, the Eagle project, it simulates the universe, and we can see the filaments here in the background. And for each of these filaments, there's thousands of galaxies in there. So by putting these constraints, we also constrain the evolution, and we see how well these simulations can produce the real universe and the real processes that we see. And the ongoing advancements in technology will allow us to get a step closer to understanding these processes and having a better understanding of our universe as a whole. So that was the first part of the talk, a more technical part. I hope you enjoyed it, and now we could have either a discussion or some questions on this part, if Ross wants to join.
Yeah, I'm back. That was awesome. I have got a question from someone. It doesn't really relate to what was going on there, but someone's 9-year-old son, Aston, wants to be an astrophysicist and an astronaut. So two really big life choices there. And he just wanted to know, what would you say is the most important subjects to learn at school to get maybe into this field or be an astronaut?
Yeah. Oh, so that's very cool, because actually when I was around 11, I wanted to be exactly the same, an astrophysicist and an astronaut. So you need to probably take maths, physics, chemistry. These are all sciences that really help you understand what is happening in the universe through physics, through chemistry. Maths, of course, is involved. So I think these would be the 3 main subjects to take. And good luck with that as well.
Yeah, that's quite a few.
Astrophysicist.
I don't think I'd manage that myself. I've got, what makes you the most passionate about astronomy? What is it about astronomy that you get passionate about and you enjoy?
Oh, so many things. Probably knowing that we don't have the answers to everything. The more we learn, the more questions arises. So we keep constantly have to ask ourselves, what is happening? How can we explain this? How can we advance? You know, and so many telescopes that are being built and have been built have revealed so much new stuff about our solar system, about the galaxy, about the universe. So I think this mystery about it, knowing that there are so many unanswered questions, just keeps me motivated and going and interested. There's always something new to learn.
Yeah, that's what I always find with just the normal, boring astronomy I do. Every time you go out there and look up, there's something different or something happening, or
yeah.
Great. Someone's just asked, do you think it's a good idea for humans to settle on Mars? That's always something that's asked at the moment, because I think people are really interested in, you know, what's going on and the fact that we're going to go back to the moon, hopefully, and go and pop and see Mars.
Yeah, I mean, every advancement that we have in space sector is a huge advancement for us as a whole, as, you know, as humankind. So it's definitely something important and great. And hopefully this will be possible. It gives loads of opportunities, not only for us as a humankind to move between different planets, but also in terms of astronomy and astrophysics, setting up telescopes on a different planet and having these long baselines for, let's say, radio astronomy and all that kind of stuff. I mean, I am excited about these sort of aspects, as I'm sure many people are as well.
Yeah, I'd like to go, but I'm not sure I'd be able to stomach sitting in a ship with people for that long at the moment.
Yeah.
Someone else asked, do you think there's life elsewhere in the solar system? Which is another one that we all want to say yes, and we want to see them, but we haven't found anything yet, have we? Not yet.
That's another big question in astronomy, right? It's dark matter, dark energy, extraterrestrial life. In the solar system, I'm not sure. I mean, of course, we don't know, so we can't say yet. And that's why there's so many missions going to different either planets or the moons of other planets to see. But as a universe as a whole, there's billions of stars in just our own galaxy, and there are billions of galaxies out there, billions. So to be honest, the possibility of there being some sort of life, some microbial life, I think is pretty high. The question is, are there any hurdles for life to evolve to more conscient beings like us, advanced beings? On that sense, of course, I don't know. But I think microbial life and that sort of simple life is quite a high chance of it being there.
So when we find it, a lot of people are going to be disappointed, aren't they? The general public are going to be like,
it would still be, everyone
would
would be amazed by it, even if we
I
found
would be.
Yeah.
Someone's asked, have you any thoughts on that comets may have been the thing that seeded life on the Earth from billions of years ago?
Yeah, that's one of the hypotheses, that comets could have been the start of life in our own planet. And I think, it's hard to tell because we can't go back in time like this. Our own, the only laboratory that we have is the universe that we see now. So it's really hard to know whether it could have happened, right? But that is one of the hypotheses of how life could have emerged on our planet. That's definitely one of them, because there are chemical footprints in the comets that could start life on planets. Yeah.
Right, two more by the looks of it. One of them's kind of about life again, and then one's more fun for you. With the limitations of traveling faster than the speed of light, do you think we'll ever be visited by aliens?
Yeah, I mean, that is a good question. And that's a question that, of course, I don't have an answer to. And I think none of us have an answer to, but it's fun to think about it. The vastness of space definitely puts boundaries on what can be achieved, at least with what we know, right? What we know now. That doesn't mean that we know everything about physics and about the universe. Maybe there's some shortcuts, like theoretical, wormholes, that you could travel through space quicker, through different galaxies quicker or something like that. But that is, again, just theoretical. So right now, it would be really hard, because even the galaxies and the stars that we're looking at, we see them as they were millions and billion years ago. So even if there are civilizations there now, we wouldn't be able to see them, and they wouldn't be able to see us. But who knows? If they're way more advanced, maybe someday, maybe.
Oh, right. There's two. One more just popped up. So the nice one is, what's your favorite galaxy? Have you got a favorite, and why?
So I'm studying these very extreme galaxies, which form stars thousands of times quicker than our own galaxy. So these are extreme stellar nurseries, and they're observed quite in the distant universe. So I think at this time, they are my favorite because they're these extreme environments where new stars are born. So these are stellar nurseries, but not one particular galaxy. If I had to choose one particular galaxy, I would be boring and choose Milky Way because we know life exists in the Milky Way.
Yeah, there's nothing more special at the moment than us, is there?
Yeah, exactly.
And then the last one is, are you using data from the Gaia spacecraft to help modeling the galaxies or modeling of your galaxies?
So I personally don't use the data, but I do know people who use the data, and that telescope is is widely used to model these sorts of things and to help us understand the physical processes and the universe and galaxies better. So there's definitely astronomers using loads of data from these telescopes to learn more about the universe. Yes.
Awesome. Cool. Well, some more might come through, but did you want to carry on to the next bit?
Sure, yes. So the next bit is a bit less technical. It's a bit more chill out. And I mean, if you have any questions at any point, I think that's fine to ask that because it's, it's just a personal view of being an astronomer. So.
Well, I'll jump in at bits then when I see questions coming through.
Yeah, sure.
Okay, no worries.
So day-to-day astronomy. So probably many people imagine astronomers as sitting in a telescope day and night, just collecting data. But actually, that's not the reality. In reality, we sit in the offices in front of our computers for most of the day, analyzing the data. Now, that is exciting. I know that might sound boring, but it's actually really exciting. So we start the day by reading some papers. In astronomy, new papers come out every single day, and they have maybe, new advancements in any techniques that we're using or some exciting results that they found. So keeping track of these advancements is really important, and keeping track of where astronomy is headed. So we usually take a cup of coffee and read those papers as we start the day in the morning. Then most of the day is used to do data analysis and programming. So basically, we get the data from the telescope, and then we spend quite a lot of time reducing that data, measuring uncertainties, finding how to interpret the results that we get. And this analysis uses a lot of programming. So a smaller but a very important part is attending meetings and conferences. And that's where you can present your science, you can present your results, and importantly, get some feedback and get some different perspectives from other astronomers and your collaborators. And astronomy, as we mentioned right at the start, is an extremely collaborative science. So I have collaborators from all around the world: Taiwan, Japan, China, America, Canada, Chile, Spain, France, Germany, just to name a few countries. So it's really important in science to have these collaborations and have different perspectives, and that's how we advance the science best. And most of astronomers are teaching courses either in physics or astronomy, or running labs or supervising students, because most of astronomy positions are at universities or at institutes that are affiliated to universities. So that's what our day-to-day looks like. But I know that most of you are interested in this small part of astronomy that is observing. When I say small part, that's not a small part in astronomy as a whole. Telescopes are running every single night. But for an astronomer, most of the time is taken by doing these things like data analysis, programming, writing papers, going to meetings. But let's talk about observing. So that's a very different aspect than our day-to-day routine. It's basically all upside down. So I'm going to talk about my experience in Chile and Hawaii. So that takes around 30 to 40 hours to travel to. And once you're there in these very remote areas, which are great for observing because you're at high altitude, which means you're above most of the turbulent atmosphere that is interfering with your results and observations. You're in dry environment, which again helps with turbulence in the atmosphere, but that means you have to travel to them quite far away from UK at least. And you get one night when you're there or you can request 2 nights to acclimatize yourself. So to basically swap your routine to work throughout the night. And these observatories, they run a very tight schedule. So no telescope time is wasted. Everything is counted from minutes to seconds, all the calibrations, all the telescope movements. So we don't want to waste a minute because telescope time is very precious. So that means that observing night can take up to 14 hours. And we go there before the sunset to make sure that we can calibrate and prepare the science observations with a telescope. And so these 2 pictures are from Mauna Kea in Hawaii. And on the left is a really nice sunset on one of the nights of observing. I know it's cloudy, but it was a beautiful sunset. And here we see 2 radio antennas as well. So these are different telescopes. And so we get there at around, let's say 5 p.m. to just set everything up and start the observations. And I had a free minute to snap this photo. And after the observations, after the whole night, we usually leave when the sun is already quite high up because, as I said, telescope time is precious. So we run up to literally the last minute that we can before sun is too high and our observations are affected. So we close up the telescope and leave at around 8, 9 a.m., which makes around 14 hours of working throughout the night. And this photo on the right was taken on the last morning of the observations before leaving, and it was a beautiful, beautiful day. So the environments are quite different. So here in Hawaii, this photo shows that, you know, when I say that I'm going to Hawaii, most people laugh and say, oh, that's not a job. You'll just sit on a beach sipping cocktails, you know, maybe running some commands on a computer. But my suitcase was mainly gloves, hats, wool jumpers, jackets, all that, because these observatories are at an altitude of 4.2 kilometers. So they're very high, and as you can see, it's snowy, it's cold, and you have to spend the whole night there as well. So it gets cold. So we observed here at the telescope that is the biggest on the right. This is James Clerk Maxwell telescope. It observes in sub-millimeter wavelengths, so around 450 and 850 microns. And the control room is within the dome, so within the wide bit, the top bit of the telescope. And these parts have to be kept at a similar temperature as outside, so there's no thermal fluctuations that can affect the telescope. So it's pretty cold even when you're in Hawaii. And my experience in Chile was very different, yet kind of the same. So the telescope, very large telescope, is in the Atacama Desert in Chile. And it's very hot there, of course, and very dry. So both places are very dry with relative humidity, I think an average of around 20% or lower, compared to around 80% in UK. So these are very dry environments, and when I went to Atacama, it was quite hot as well. Although at night, again, it got cold and I had to wear jackets. So it's quite a bit of a varying in temperature. So where do astronomers live when they go observing? Well, for the Very Large Telescope, VLT, you have this residencia, which is basically a hotel for astronomers. So because the telescope area is around 100 kilometers or 150 kilometers away from the nearest town, astronomers had to have this hotel to actually be able to observe there. And to make it more normal for people to actually be there and relax and get a good night's sleep, they needed a higher humidity. So there's a lot of plants inside, and there's a pool, and every room has a humidifier to make it easier for you to adjust to get some sleep before the observations, basically. And this was one of the first nights when I went there before I had to go to the telescope. So of course I wanted to change my routine to be working at night. So I stayed up the whole night and just took some photos of star trails in the desert. And observing in Hawaii, on Mauna Kea, is very similar. So you're staying at around 3,000 meters altitude, but of course the environment is quite different. You see a lot of plants and greenery around, but basically it's the same thing, that you get a room, you have basically a kitchen where people make you food, and you have a lounge area where you can relax and sleep and get a good night's sleep before your another 14-hour shift. Now this was supposed to be a bit of a GIF, but I think it doesn't work. Anyway, so how do we observe, and what are the control rooms like? Well, the two places were slightly different. So on the left here is, as I said, the control room in the dome of the telescope in Mauna Kea in Hawaii. So we monitor the telescope, how it's doing, what science it's doing, and also we're monitoring the atmosphere, because it depends what projects we're doing on the atmospheric conditions. And on the right here is the control room of Very Large Telescope. And those control rooms are not within the telescope. This is a different building where all 4 telescopes have their controls in these separate sections. So 2 of them are shown here. So basically all the people from from all these 4 different telescopes are working together in this one room. So hopefully you're seeing the video. I got a free minute to go outside and put my camera down to take some videos of VLT, the Very Large Telescope UT4 unit, which has 4 laser guide stars that you can see here in orange. And these create artificial stars to help calibrate and take into account the atmospheric turbulence, so that we can get better resolution, better images of objects that we're trying to observe. So I basically just put the camera out there and went back to the control room to observe while it took these observations over the whole night, these pictures over the whole night. And also astronomers kind of find it fun to make funny videos with us. So hopefully the sound will work on this.
This is now the ultimate power in the universe. I suggest we use it.
So yeah, this was a video made by my supervisor, just using a GoPro camera at the Very Large Telescope, where we use the Muse instrument. So yeah, we're having some nerdy fun out there as well. And these are just some nice pictures that we managed to get. So sometimes the observations, the atmospheric conditions were not good enough to make our observations. So we kind of went outside to look around as well. But one fun fact is that actually for our human eyes, being at 4.2 kilometers up doesn't really help us see the stars better. For telescope, it's amazing, but for our eyes, because there's not that much oxygen going to our eyes, we can't really see it much better, and we should be staying lower down at around 3 kilometers. We will see stars much clearer and much nicer than at the top of the telescopes. So that's what we kept telling to people who kept coming to observe the sky. We said, please go a bit lower down because you'll actually see the sky much better. And the sky is amazing there, both in Hawaii and Mauna Kea. I don't know if you have any questions at this time about any aspects of observing or going to these places.
Well, there is one about when the ELT is built, will you be using it?
Yes, definitely. That's that will have huge advances and huge implications to a lot of astronomy areas, including mine. So I'm definitely waiting for that. And actually, when I went to VLT, we saw the concrete being put on top of the mountain where ELT will be. And that was extremely exciting because this will be very different. It's a 39-meter primary mirror, which means that we can collect so much more light. It will have adaptive optics, which means that it will almost be like observing from space. So we have this huge telescope with huge resolving power, which will allow us to look deep into space and deep into distant objects to detail that was never been possible before. So that's definitely one that I'm looking forward to.
There's one asking about, not sure you'll be able to use it yourself because you probably can't go to space, but you probably can. But what's the James Webb going to teach us over Hubble? So like what's better about it really, I'm guessing, or?
Right, yeah. So yes, James Webb will be an amazing telescope. One difference is that it's observing in the infrared while Hubble is observing in the optical. And so as I've shown before, there are certain differences that you are observing, different physical processes that are happening. So with visible, you're looking at stellar populations, at stars. With more infrared, you're looking at more dust, more hot dust, star-forming regions, or active galactic nuclei, which are these accreting black holes. So it will give us a very different perspective of the same objects that Hubble is. So I wouldn't say it is better than the Hubble, it's very complementary to Hubble. So both of them will be still very much used and very exciting. And I'm definitely waiting for James Webb, and hopefully it will happen this year because we got a timetable of what science it will do, and it will help me to understand more about dark matter through my studies as well.
So, is there another telescope you'd like to visit?
Oh, so many. So there's a telescope in the South Pole. That one is an extreme one, of course, because you have to go there for a very long time and not many people get to go there. And I think even though it's somewhere that I would want to go, I don't know if I would actually go if I got the chance, because it's almost as secluded as being on the International Space Station, which is cool and terrifying at the same time.
Get a taste of space then and being...
Yeah. Also other ones like La Palma in Tenerife, it's very different. I think every telescope and every place that you go to has its own, exciting bits. So wherever I can go, I will go.
Someone asked, have you made a discovery yourself?
So that's a big question, because every study in astronomy brings in some discoveries and some new science that we can learn about. So in that sense, yes, I have made some discoveries and some new aspects of galaxies that we didn't know before or haven't looked at before. In terms of these huge new leaps in science, these come about not very often. So in those terms, I haven't yet, but maybe. But we definitely learned more about galaxies and their evolution and how they evolve into galaxies we see today, much more, of course.
Cool. Someone's asked, is it better if you wear an oxygen mask? I'm guessing, was that about the site observations?
Yes, yes, that's definitely a thing. So especially in there's higher altitude sites like ALMA, which I've shown you before, this radio telescope array, which is at 5,000 meters altitude. And some people do wear oxygen masks, although it's not very, it's not recommended. So in our telescopes in Mauna Kea, where I went, they said that if you need to use an oxygen mask, then you should go to lower altitude because your body can't take it, basically. So what we do is we check our blood pressure and heart rate using this small finger clip thing to just check throughout the night how our bodies are doing. And we use a breathing technique if we feel a bit dozy or something. So there are ways to cope with it, and most people cope with it all right. But of course, you wouldn't be recommended to run around the telescope a lot because that would make you feel out of breath and a bit fainty.
I never knew any of that, so that's really cool. It's actually, in a way, slightly dangerous, a bit of a risk to you.
Yeah.
I think there's the last one here. They said, was it disorientating when you looked up and saw like the southern hemisphere stars because it's all different, just like using your eyes?
Yeah. So it was amazing to see it for the first time. I mean, anytime you look up at the sky, it's amazing. But to see the differences, the Magellanic Clouds, the Milky Way bulge and the Southern Cross, all of that is so different to what we see in the Northern Hemisphere that, you're just like, wow, how vast is, the sky and what we can see with just our own eyes. So that definitely was something that was really cool and different.
I've found it trouble just when I go to a dark sky site and I can actually see all the stars. You lose the constellations.
Yeah, there's too many.
What?
Thankfully, for telescopes, we have a coordinate system. So similar to land systems that we have longitude, latitude, we have a system for the sky as well. So telescope automatically knows where to point if we put in these coordinates. So we don't manually need to actually look at the sky to point the telescope there.
That's good. So, well, with the seconds, every second counts. You don't want to spend half the night trying to find something.
Yes.
Waste all that time.
Yeah.
Cool. Someone just said, never heard such a complex subject explained so simply. So thank you very much.
Oh, I'm glad you enjoyed it.
So that's I think that's all the questions, and that's pretty much an hour or so of your time. So all I can say is thank you so much for, giving us an insight on what it's like to actually be, a proper astronomer as opposed to us garden astronomers. So thank you very much. And if there are any questions, feel free, if you're on the Facebook, to answer them, or we could jump in there as well and try.
Yeah, please, if you have any other questions or you think about them later on, if you put them in the chat, I'll try to keep track of them and answer them later on as well. So, yeah. Awesome.
Well, thank you very much. Cheers, guys, for watching and listening. It will be there for the rest of the night, so you can go back and enjoy it and then put it onto our YouTube channel. So thank you very much, everybody. Take care and clear skies.
Thank you.